Hello dear students, today we are going to discuss about power of a lens. Power of a lens is the measure of the deviating strength of a lens. What is this deviating strength called? When light radiation is made to pass through a lens, the extent to which, or otherwise I can say the degree of deviation of the light ray produced by the lens is called power of lens. The degree of deviation of the light ray passing through the lens is called power of lens. So when light radiation is meant to pass through a lens, the light radiation is getting bent from its original path. The extent to which, the extent is termed here as degree. Degree here refers to it doesn't refer to the angle, it refers to the extent. The extent to which the deviation of the light radiation is produced by the lens is called power of lens. So we can say it is the measure of, the power of a lens is the measure of a deviation or deviating strength, you can simply say. Measure of deviating strength of the lens. So power of the lens is the measure of deviating strength of the lens. That is, it is the amount of or the degree of deviation produced by the lens when light radiation is made to pass through it. This is called power of lens. In other words, we can say power of a lens is inversely proportional to the focal length of the lens, or power of a lens is the reciprocal of focal length. What does this mean? If the lens has a greater focal length, the power of the lens is less. If the focal length of the lens is less, then the power of a lens is more. So we can say here, the power of the lens varies inversely with the focal length. Greater the focal length, lesser is the power of the lens. Lesser the focal length, greater is the power of the lens. So we can put it in a different form. If power of lens is more, deviation produced by the lens is more, so the focal length is less. If power of lens is less, deviation produced is less, focal length is more. We can understand it with a simple diagram. You consider this as the first diagram where I am using a thin lens for which the deviation produced is, let us say, θ1, and the point through which the light radiation is passing through after getting refracted from a lens is called principal focus, and the distance between the optic center and principal focus is called focal length. Let me mark this as focal length f1. Now I am taking another lens which is a little bit bulky, and a ray is passing through it. This is the original path of the light radiation, and then it gets deviated along this path, and this is the principal focus of the lens. This is the optic center, and the focal length is said to be f2. We just look at the case here. This is the angle θ2. When you compare these two angles, θ1 and θ2, θ2 is much greater than θ1. θ2 is much greater than θ1. Let me mark this lens as 2. So we can say power of the lens 2 is greater than power of the lens 1, which means deviation produced by the second lens is more than the deviation produced by the first lens. In other words, I can say power of the second lens is more than the power of the first lens. If power is more, what happens to the focal length here? Focal length is getting decreased. So focal length of the second lens is less than focal length of the first lens. Focal length of the second lens is less than the focal length of the first lens. So we can compare the power and the focal length of the lenses which are varying inversely. Power of the lens varies inversely with focal length. So greater the focal length, lesser is the power of the lens. Lesser the focal length, greater is the power of the lens. Power of the lens can also be defined in other words, like power of the lens is the measure of degree of convergence or divergence of the light radiation passing through it or passing through the lens. When light radiation is made to pass through a lens, power of a lens is the measure of degree of convergence or divergence of the light radiation passing through the lens. Degree of convergence or divergence. Degree here, once again, as I told you, degree of convergence here refers to the extent to which the light radiation has been converged or made to meet at a point, or diverged, made to spread out from a lens. So the power of a lens can also be defined as I told you, this is defined as the measure of deviating strength, or in other words, I can say it is the measure of degree of convergence or divergence of light radiations passing through it. Light radiations passing through it. So we can say. And also, power of a lens can be defined as the reciprocal of its focal length. Power of a lens can be defined as the reciprocal of its focal length. P equals 1 divided by F. Once I am repeatedly saying the same thing. Once, or in one way, you can define power of a lens as the measure of degree of convergence or divergence of the light radiation passing through it. Or in other words, I can relate it with focal length, that the power of a lens is the reciprocal of its focal length. Once again, greater the focal length, lesser is the power, lesser the focal length, greater is the power of the lens. Power of the lens is positive for converging lens or convex lens, and power of the lens is negative for diverging lens or concave lens. So power of a lens is positive for converging lens and is negative for diverging lens. So we can say if power is positive, focal length is also positive. If power is negative, focal length is also negative. So we can say power of a lens is positive for converging lens and is negative for diverging lens. And you can say the unit of power of the lens is diopter. Unit of power of the lens is diopter. 1 diopter equals 1 meter inverse. 1 diopter is equal to 1 meter inverse. Unit of power of the lens is diopter. 1 diopter is equal to 1 meter inverse. 1 diopter is equal to 1 meter inverse. Reciprocal of meter is 1 diopter. Either you can represent the equivalence of 1 diopter in terms of meter inverse or in terms of centimeter inverse. If it is in terms of meter inverse, power of the lens is equal to 1 by F. If it is in the terms of centimeter inverse, the same expression can be represented as 100 divided by F. Simple. So power of a lens is 1 by F when it is represented in terms of meter. Power of a lens is 100 by F when it is, or when the same is represented in terms of centimeter. 100 divided by F. Also, with the help of lens equation, with the help of lens formula, I can express the power as P equals 1 divided by F, which is equal to n minus 1 into 1 by R1 minus of 1 divided by R2. With the help of lens maker's formula, we can write the expression for power of a lens as P equals 1 by F, which is equal to n minus 1 into 1 by R1 minus of 1 by R2. Here n is the refract index of the lens. Refract index of the lens. R is the R1 and R2 are the radius of curvatures of the surfaces of the lens. Radius of curvature of the spherical surfaces of the lens. So we can compare the power of the lens with the refract index of the material of the lens, as well as we can compare power with the radius of curvature of the lens surfaces. So we can say here, if the refract index is more, I can say power of the lens is varying directly with the refractive index. If the material has greater value of refractive index, if n is greater, then the power of the lens is also greater. Power of the lens is also greater. If refractive index is more, power of the lens is also more. What does this mean? If the material has a greater refractive index, we can say the material with which the lens has been made is dense. If it is more dense, then we can say when light radiation is made to pass through that particular lens, deviation produced by that lens will be more. If deviation produced by the lens is more, power of the lens is more, focal length will be less. So if n is greater, P is greater, F will be lesser. If n is lesser, we can say power of the lens is n is lesser, power of the lens is lesser, focal length is more. So this is the relation connecting power and the refractive index of the lens. We can also speak about power and the radius of curvature of the lens. Power varies inversely with the radius of curvature of the lens. We can simply say here, if you consider a thick lens or a lens which is bulky, you can say a bulky lens or a thick lens has a lesser radius of curvature. If you consider these spherical surfaces, the radius of curvature, let us say this is R1 and this surface has a radius of curvature, let us say R2. So the values of radius of curvature is less here. If R is less, you can write if R, radius of curvature is less, lens is bulky, power of the lens is more. Power of the lens is more. Which means if you use thick lenses for deviating the light radiation, then the light radiation can be deviated to a greater extent. If you use thick lenses whose radius of curvature is small, then the power of the lens is more, which means the deviation produced by the lens is more. Deviation of the light radiation produced by the lens is more. So for bulky lenses, radius of curvature is smaller, power of the lens is greater, which means the deviation produced by the lens is more. For skinny lenses, we can say here, for skinny lenses, if the lens is thin, then we can say the radius of curvature is more here. For this one, this is a greater sphere and this is a part of the spherical surface. So the radius of curvature will be more here in this particular case. Let us say this is R1 and this radius is, let us say, R2. So the values of R1 and R2 is more here. If the radius of curvature is more, then the power of the lens is less, which means the deviation produced by the lens is less. So for skinny lenses, we can say here R is more, so P is less. Power of the lens is less. So radius of curvature is more, power of the lens is less. You can say deviation produced by the lens is less. Thus, we can arrive at a conclusion. If you are using thick lenses, then the power of the lens is more. If you are using thin lenses, then the power of the lens is less. That's the idea. That's the simple idea. For thick lenses, focal length is less, power is more. For thin lenses, focal length is more, power is less. Thus we can conclude. So what is power of lens? It is the measure of degree of convergence or divergence of light radiation produced by the lens. Or in other words, we can say power of a lens is the reciprocal of focal length of the given lens. We shall see an example problem now. Example 6.16. If the focal length is 150 cm for a glass lens, what is the power of the lens? As we saw by the definition, the power of the lens is reciprocal of focal length. So this is the formula, P equals 1 divided by F. The focal length of the given lens is 150 cm. When converted into meter, I will have 1.5 meter. Then the power of the lens can be calculated as P equals 1 divided by 1.5. Instead of focal length, I am substituting 1.5 meter. 1.5 is nothing but 3 by 2. So I will have 2 by 3. 2 by 3 is 0.666 diopter. I can round it off to 0.67 diopter. Or in other words, I can write it in terms of meter inverse. Power of a lens is 0.67 diopter. As the power of the lens is obtained positive, as the power of the lens whose value is obtained positive, we can conclude, we can arrive at a conclusion that the given lens is a converging lens or the given lens is a convex lens.